Okay, physics. I want to talk through a couple of cases of uniform circular motion that are a little bit trickier to think through. The principles are still the same and there's no new math, but diagramming and thinking these through is really the challenge. So first I want to talk about what happens when you're swinging something up and down in a circle. So suppose you're standing here you are, and you're swinging something that's on a line perhaps, and it's going down and then back up again. Right? So imagine that's a circle. So let me turn it sideways. So what we're looking, something going in a circle, right there you are standing in the background, and we're going to think about 4 points on this here, and we're going to make 4 different diagrams, A, B, C, D. All right, so importantly, there's nothing new here, but I just want to remember, so this thing is connected by a line that's providing tension. So my centripetal force is my net force. So, and the key thing with this is that the centripetal force is not a real force, it's a net force, so it's going to come from, it can come from a variety of places. So let's think about this. So I'm at position A, so I'm going to make a force diagram for what's happening at position A. Well, let me think about this. So I've got tension pulling down, so the string is holding it. If this has mass, which it needs to, that I also have gravity pulling down. Right? So the sum of my forces are going to be gravity plus tension, and that's going to equal my centripetal force. Let me go to B. So at point B, what's going on at point B? Well, at point B, here's my bob. I'm going to have gravity pulling it down this way. I'm going to have tension pulling it this way. So what's the net force to make this go in a circle, right? So my center seeking forces, what are the things that are making this go in a circle? Well, the sum of my forces in the direction that we care about, right? So the center seeking forces are going to be in this dimension. So my force of gravity is perpendicular, it doesn't affect it. So some of my forces in the dimension I'm interested in is just going to be tension, and this is going to equal my centripetal force. So notice that my centripetal force here, it must be the same, right? So it's going in uniform circular motion. So that net force, the centripetal force to keep it going, remember, so one way to look at this, so my centripetal force is going to be mass times centripetal acceleration is V squared over R, right? So my mass times centripetal acceleration, so it's going at constant velocity, so this force is going to be the same, meaning that here my tension is going to be greater than it is here. Right? So here I have gravity helping me, and here gravity is not playing any role. I get to part C in my graph here, so at the bottom here, now I'm going to have force of gravity going the opposite way of tension. Right? So I want to be careful about the signs here. So I'm going to make towards the center be positive. So notice what I did up here. So I made towards the center be positive. These are both pointing in the same direction. Now when I sum my forces, I'm going to have towards the center be positive. So tension is going to be positive, and my force of gravity now is going to be negative. So you saw what I did there, right? So at the top of the arc, force of gravity is going in the same direction as tension. So it's adding together with tension to provide the centripetal force. And here at the bottom, force of gravity is going the opposite direction of tension. So in the same diagram, I've given gravity 2 different signs. Yeah, I know it's tricky, but we're worried our frame of reference is going towards the center. And then lastly, point D is going to be very similar to B, where force of gravity is not going to factor in. So when you have things going in a vertical circle, that depending on where you are in that circle, that centripetal force is going to come from a different place. Sometimes it will be entirely from tension. Sometimes tension will have to fight gravity, so it will be stronger. And sometimes at the top, tension will be less. And a lot of times I will say something, well, it just has just enough speed to make it around in a circle. And what we mean by that is that at the top of the circle, my tension is going to be 0. So that means at the top of the circle, all of that centripetal force is coming from the force of gravity, and that's just one of the clues that we get into. So, so that's going in a vertical circle. So the other thing that happens, so let me go back to this thing I mentioned last time. We're going in a horizontal circle. So let's see, so I'm going to go here. Yeah, so here's my guy. He's going in a horizontal circle. So notice how this is shown going at a perfectly perpendicular angle, right? And that just doesn't happen, right? So this bob has gravity pulling it down, and this is not a perfectly perpendicular angle. So let me talk through that. So this is what we call a conical pendulum. So it's going to be something that's going in a circle and uniform circular motion. And some important ways to think about this. So let me go back to the piece of paper here. So a conical pendulums, right? So here's my pendulum. So let me exaggerate this, right? So here's my circle, and my pendulum is hanging off at an angle and going around this pole in a circle. There's going to be some angle in here. So I've just exaggerated what is happening, but no matter how hard you spin that, no matter how fast you go, you'll never get it to be perfectly horizontal. And think about this, right? So I'm going to draw a free body diagram for this. Okay, so where it is over here. So here's my bob. Right? I'm going to have force of gravity pulling it down, and what else is touching it, right? So gravity's acting remotely. The only thing that's touching it is tension, right? So my free body diagram has these two things. Again, do not put centripetal force on a free body diagram. It is not a real force. So I'm going to think about what's going on here. So I make a component diagram. I'm going to break tension up into two. So I'm going to have a horizontal and a vertical component of tension. Right? So I'm going to have force of gravity, and I'm going to have my component diagram now. So tension in the vertical dimension and tension, I'll say, in the horizontal. And these two are going to balance each other. Those two cancel each other out, so it's not accelerating up or down, right? And by acceleration, I mean it's not increasing speed and it's not changing direction. Right? So it's staying at the same level vertically. But what is changing direction going around horizontally, right? So now my tension in my horizontal component is my centripetal force. And now this is equal to my mass times centripetal acceleration, and I can replace centripetal acceleration with Vt squared over r if I wanted to. So I can have a way to get to figure out what the velocity is, or if I know velocity, I can figure out what the tension is, but recognizing that I'm only discovering one component of the tension, I need the angle and some trigonometry. The SOHCAHTOA, the Native American goddess of trigonometry, can help you get there, but you gotta make this connection. So this is a pendulum. So the important thing, though, is that my centripetal force is going directly towards the center. And this becomes important when we get to something like cars, right? So why does your car turn? Well, there's got to be some net centripetal force that makes your car turn. So here we go. So here's your car on the ramp, right? I've got tires, right? And I've got friction acting on those tires, right? So which direction do the tires want to go? So if you're making a turn, so here's you going around a turn. This is a banked curve. Right? So your tires want to slide down. So my friction is going to be going up. Right? So I'm going to have a couple of things. I'm going to have gravity pulling down. And I'm going to have the normal force of this pushing up on this. Right? So if I was to draw a free body diagram, usually when we see a ramp, we would want to rotate our axes of rotation. But importantly, centripetal force is that center seeking. So I'm trying to find what is, right, don't draw this on it. So what is my net force that provides the centripetal force? And it's going to be center seeking. So this is the one case where you do not want to rotate your axes. Right? So in this case, I'm going to keep my axes. What I want to find is this dimension. I'm going to separate my normal force going off at some angle. Some fraction of that's going to, that's my normal force. That's my force of gravity. And depending upon how fast you're going, I could have friction going up the hill. I could have friction going down the hill. I don't know. It depends how fast you're going. So I have some force of friction. So in this case, I have to go through separating two of these into components to figure out the net force that's going towards the center. I don't want to rotate the axes. So again, similar to a conical pendulum where you've got to separate things to find the net force is going towards the center, but it has an extra trick to it. Okay, last thing I want to mention was the gravitron. So I don't know, maybe you've been on this ride. Right? Here it is, right? So they put you in this spinny thing that goes around, and as it goes faster, you get to a point where you can balance, right? So look at this guy. I don't know, you can make this out. That's crazy. So he's standing up, right? This is spinning around, and he's being held by something. So Let me talk you through what's going on here. So again, something's providing that centripetal force. What is it that's providing that centripetal force? So, so here we go. So here's oh, lost focus there. Come on, focus. Okay, my gravitron. So I'm going to think about this. So I'm going to look from the top down first, and I'm going to have some person here, and there must be something that's providing a force to move him towards the center, right? So notice when I'll turn this sideways. So let's look at here's my person as he goes around on the gravitron, right? And here's the center. So let me think about the forces acting on him. Here's my free body diagram, right? So I'm going to have something providing a force to make him go in this. So when we think about this, the only thing that's touching him is the wall of the gravitron, right? So that wall of the gravitron is providing a normal force, right? So as he comes around, right, his body wants to keep going straight, but the gravitron wall is pushing him to change direction, right? So it's a normal force coming from the wall, right? There's mg pulling him down, but he's not going down. So what must be holding you in place? Well, what's the only thing that opposes motion? And that's going to be friction. So I must have friction opposing that motion of the guy falling down, right? So these two must be equal, and I have a net force, in this case a normal force coming from the wall, that must be holding him in place. So fundamentally there's still the same idea. I have a centripetal force. This is coming from the normal force in this case, and I can use the normal force to calculate friction or vice versa, so usually there's some connection that can be made there. But notice that these perpendicular forces don't factor in. It's only those forces that are center or away from center, so in that same dimension, and only those forces are the ones that that make a difference and add into the program. So anyway, I hope that's helpful. So a couple of applications for uniform circular motion. Again, same idea. So we're going to have centripetal force. Don't put it on a force diagram. It's not a real force. It's a composite force. And then we use the same equations. So we use Newton's second law for uniform circular motion. So my centripetal force over my mass. We have centripetal acceleration is tangent of velocity squared over the radius. And then if we need to, we can calculate my tangential velocity as being the distance you travel, use capital R, the distance you travel all the way around divided by the time it takes to make one cycle, or the period. So with these three, you should be able to get everywhere. I hope that helps. Talk to you soon. Bye.